Hi, we're ready to start talking about section 18.3, which is reversible reactions and equilibrium. Okay, we're going to talk about reversible reactions. We're going to talk about what happens at the molecular level in a chemical system at equilibrium. We've already talked about chemical reactions, and we might think that they only go in one direction. But this is not entirely true. Some reactions are reversible. In other words, we might make some products, but then some of the products go back to become reactants. It's kind of like if you have a Mounds bar and you add some almonds to it, you have an almond joy. But if you take the almond away, you basically have a Mounds bar. So that's kind of what a reversible reaction is. So here's two examples. We have sulfur dioxide plus oxygen makes sulfur trioxide, but sulfur trioxide will decompose into sulfur dioxide and oxygen. If we look at this, we can say the first reaction is the forward reaction. And the reverse reaction will be the second reaction. So this is R and this is F. Okay? So many times we're used to be looking at the forward reactions, but in equilibrium we have some of the products going back to reactants, so there is a reverse reaction. We can rewrite these two equations into one equation, and instead of worrying about writing two, you know how I always say chemists don't like to waste ink. Well, we make these two half arrows, signifying forward and reverse. This also is a clue that the equation is reversible. Let's look at a picture of this. Here's our SO2 and O2s. Our O2s are the two red atoms, and the SO2s are the red and yellow atoms. When they react, we'll make some SO3s, and we might still have some oxygens left. But then the SO3s can break down and to some oxygens and some SO2s. So our equilibrium position would be in the middle. So here we have an SO2, here we have an O2, so there's our SO2, O2, and here's an SO3, here's another SO2. So basically these are forming here some SO3s, and eventually some of these make SO3s, but then some of these SO3s break down. So we're going to be somewhere in this area eventually where we have an equilibrium. But what happens is this is called a dynamic equilibrium because this is constantly happening. So this could be changing to an O2 and an SO2, whereas then you could be making two other ones back into this. So to the eye, it looks like the same concentration, but actually at the molecular level, they keep on changing places. So equilibrium has to do actually about rate. So the rate of the forward and reverse reactions are equal. That's when we're at chemical equilibrium. They're still reacting, but the rate is equal, so you're not seeing a change in concentration of the products and reactants at equilibrium. So let's look at this graphically. So if we look at the initial concentration, we see that we have SO2 and O2 to start with, and no SO3. So if we look at our first graph, and look down here, the SO3 line is 0, the SO2 and O2 are at some value. Notice they decrease with time, and eventually they form a plateau, and the SO3 builds up, and it forms a plateau. So when we get the plateaus, we're at equilibrium, meaning that the concentration of these species do not change after equilibrium. Another scenario is, what if we're going backwards? What if we have our SO3 in this picture, okay, we have some quantity of that, but our former reactants are at 0. Again, we'll see a similar thing. This will start decreasing, and this will start increasing. But notice, at the same temperature, these values are the same. Okay? The difference is these don't cross when you have a reversal of this particular reaction, because we're already at 0 concentration. We don't have to get that far up to get above that to this line. And this has to only come down a little bit to get to the equilibrium position. Okay? So again, both have this plateau showing where the equilibrium occurs, but depending on where you're starting, these plateaus may cross or may not. Okay, let's look at an idea of equilibrium from life. When a department store opens in the morning and people are going up the escalator, most people are going up because they entered from the ground floor. Later in the day, you probably have equal number of people going up and down the escalator. Okay, to reiterate one more time. At equilibrium, both reactions continue. No net change in concentrations. Okay, concentrations remain constants, but the individual molecules themselves are continuing to react. Now, the concentrations may not be the same. So what we have is we have equilibrium concentrations, or those at the equilibrium position. So you don't have equal amounts of products and reactants. There's some ratio between them that is going to be constant. So for instance, in a scenario where we basically have some reactant A that makes product B. In this case, we see that almost all of the A is gone. We only have 1% left. So we see a big arrow going to the right and a little one returning because we have 99% of B. But what's happening is some A turns to B, but as B turns to A, then you basically have some A turning back to keep this ratio going on. If you think about putting sugar in water, when you get it, all the sugar that can dissolve, and you add one more piece of sugar and it goes to the bottom, what might happen is, yes, you have a saturated solution, but some of those little molecules that you can't see may be forming sugar and then some more dissolve, so you keep the same amount dissolved. Same idea. Okay, same idea. Okay, in principle, everything's reversible. In practicality, though, it may not seem that they're reversible. Okay, some components may be so favored that you can't see the other ones at all. Okay, so for instance, when you cannot detect any reactants anymore, we say that the reaction has gone to completion because we have mostly products, or sometimes we use the word irreversible. On the other hand, if no products can be detected, you can say no reaction has occurred, okay, because you have very little products. So we basically say no reaction occurs. But in both cases, there could be a teeny bit of product there could be a teeny bit of reactant left. Okay, why is equilibrium considered to be a dynamic state? I'll let you answer that in EduCanon, and I'll be back in a second to answer that question more fully. Okay, it's what I said before. Both the forward and the reverse reactions are constantly taking place. Okay, but the rates are equal, and there's no net change in concentrations. There's these equilibrium concentrations of products and reactants. Those concentrations are not necessarily equal to each other, but the ratio between them does not change. Okay? All right, let's go on to part 2. Will be in the next part of this video.